Greatest common factor is what we will be talking about today, humans. A common factor is a whole number that is a factor of two or more non-zero whole numbers. So, might you imagine that the greatest common factor would be the greatest of these common factors? Greatest of those, and we defined a common factor above. So what does this look like? Well, it looks like this. If you have numbers like 27, 45, and 90, and you wanted to find the greatest common factor among them, what is the greatest factor that they share? A process that we can do, so method 1, would be to list all the possible factors. List all factors of each number. Of each. So let's do that. Looking at 27, the factors will be 1. Well, 1 times what equals 27? Well, 27. How about 3 is also a factor, and that matches with 9. It's probably best to write these in numerical order. So let's match 1, 3, 9, and 27. If you look at the number 45, 1 matches with 45. 2 doesn't work. How about 3 with 15? And I think 5 works with 9. Sweet. And lastly, we have the number 90. Its factors are 1 with 90. 2 works with 45. 3 works with 30. Does 4 work? I don't think so. 5 works with 18, I believe it is. And 9 works with 10. Sweet. Now let's find which of these is the greatest that all of these share. So they each have a 1, but that's not the greatest number they have in common. 3 as well, but that's not the greatest still yet. They all don't have a 5. This one doesn't have a 5 up here, but it does have a 9. And it looks like this one and this one have a 9. So the greatest common factor is actually 9. Sweet. That's method 1. Let's talk about method 2. Method 2 requires us to find the prime factorization of each of the numbers, but is also the easiest of the two methods. Let's look. 3 with 9, this is prime, so circle it. 3 with 3, so prime, let's circle it. Here we go, on the search for prime numbers. We can split this up into 5 and 9 if we wanted to, where 5 is a prime number. 9 can be split into 3 and 3. Circle your primes. Here we go, we have 9 with 10 is the first thing I see. 9 again splits into 3 and 3. 10 splits into 2 and 5, and those are both prime. Now we would list the prime factorization. So let's shrink this little guy here, and let's list each as a product of its primes. We've got 27 that ended with 3 times 3 times 3. 45 ended with 5 times 3 times 3. And lastly, 90 ended with 3 times 3 times 2 times 5. Now that we have the prime factorization for each number, in order to find the GCF, we find what these numbers have in common. So notice we find a 3 in the first, a 3 in the second, and a 3 in the third. So I circle all that they have in common, and then once I find something that's common in every one, I write it once in my GCF. I'm on search for another number that's in common, and if I look at the factorization, I can find another 3 that each of the numbers have, so that we can write another 3 here. Notice your GCF is again 3 times 3 is 9. I'm going to do this one without any noise, and I'm going to use method 2. Notice that they didn't have any other number in common besides the 2. So the GCF between the numbers 16, 36, and 52, the greatest of the common factors is 2, the number that's the biggest that can divide them all. Nothing changes when we introduce variables. To find the greatest common factor, we need to write the prime factorization for each of these numbers. Looking at the first, 20. We can split that up into 2 times 10. 2 is a prime number. 10 can be split up into 2 times 5, where 2 and 5 are prime. 36 can be split up into, let's go with 6 and 6 again. 6 can be split up into 2 and 3, both prime, and same with this 6, 2 and 3. And you go and you write the prime factorization. I write it vertically so it's easier to see if there's any numbers that are if there are any numbers that match up. So here we go. We've got 20 is 2 times 5, and 36 is the same as saying 2 times 3 times 2 times 3. Now, hold on a second. This number isn't really 20, it's really 20x squared. And this number isn't exactly 36, it's 36x. So we can add something to this prime factorization. We can add this x squared idea. X squared is really x times x. That was easy. And here on the bottom we have 36x, so 36 is multiplying x. So let's just multiply x at the end. Same rules apply for finding the GCF. In this prime factorization, what do they have in common? They have a 2, so write it. What else do they have in common? Here's another 2 that matches with this 2, so write it. And lastly, they have an x that matches with an x, so write it. The GCF is 2 times 2, which is 4, and they have an x. 4x is the GCF. For the last example, let's find the GCF between these numbers. Recall that a prime factorization, creating a factor tree, is the first step. 32 can be split up into 2 times 16. 2 is prime. 16 into 2 times 8. Looks like we'll have a lot of 2's here. And finally 2 times 2. So we can see that 32 is the same as 2 times 2 times 2 times 2 times 2. 6 can be split into the primes of 2 and 3. Okay, now let's make this a little bit smaller so we have room. Let's go ahead and list the prime factorization of the first monomial, which is 32xy squared, which is just the same as 2 times 2 times 2 times 2 times 2. And you also have 1x and y multiplying itself 2 times. Okay, and for the second of the monomials, this is x squared with a y. And we recognize that 6 can be split into the prime factorization of 2 times 3. Also, x is multiplying itself twice, and you have a lonely y. The last step is to write your GCF as a product of these primes. What do they have in common? They both have a 2, so write it just the once. What else do they have in common? Does this one up here have a 3? No. So we can't use 3, but this one does have an x matching with this x. So write it. And it looks like this one has a y that would match with this y. So write it. Your GCF is 2xy. Yay.